Hi, this is the professor, and today we want to continue Lesson A, dealing with the linear speed of an object traveling in a circular motion. Now we're going to talk about a couple of application problems which will be very, very, very important dealing with linear speed. Linear speed on Earth and linear speed on the moon. Let's talk about a problem right here. The Earth rotates on an axis through its poles. The distance from the axis to the location on Earth's 30-degree north latitude is about 3,500 miles. Therefore, a location on Earth at 30 degrees north latitude is spinning on a circle of radius 3,500 miles. Compute the linear speed on the surface of the Earth at 30 degrees north latitude. Express your answer in miles per hour. Now, one revolution is 24 hours. Remember, one revolution is 24 hours. The Earth spins on its axis, and it takes 24 hours to complete one day. Now, let's look at this. One revolution is equal to 2 pi radians. Remember that? And what 2 pi radians is equal to 24 hours in this case. Because the Earth rotates on its axis, one day is equal to 24 hours. Now, let's talk about this particular formula. V is equal to S divided by T. Right? This is the length of the arc, isn't it? Which is S is equal to R times theta. Now, here, when we go back to here, we talk about R times theta divided by T. This is with respect to time. Now, the length of the arc here, remember, was, subtended by an angle, right, of some unknown or some particular degree or radius. However, since we're dealing with the rotation or the revolution or the rotation of the Earth on its axis, let's look at this, pretend that this is the top of the Earth from the top view. And that thing is turning, or rotating 2 pi units, or radians. 2 pi radians is equal to, again, 24 hours. And one day is equal to 24 hours. Now, with this formula here, as we see that R times theta over T, here this kind of simplifies itself to what? R times theta over T. Now, what is theta over T? That's the angular speed, right? So that is omega, which is equal to theta divided by T. Because of this now, we have a formula that's simplified to what? V is equal to R times omega, which is theta over T. Now, let's look at this very closely. We have a radius of 3,500 miles. So, still, we're looking at this formula right here, which is V is equal to R times omega. Now, we have to consider the angular speed omega here, which is what? The units is 2 pi radians is equal to what? 24 hours. So we have to set that up as a ratio because it is in miles per hour. So here, with the radius R being 3,500 miles times, here's your angular speed, omega, this is going to give you 916 miles per what? Hour. This is your solution. So this is the linear speed on the Earth. Let's do another problem. Now, if we can look at this very closely, the mean distance of the moon, you can zero in there, from a planet is 2.61 times 10 to the 5th miles. Assuming that the orbit of the moon around the planet is circular and that one revolution takes 25.1 days. Now remember, one day is equal to 26 hours in this particular case. Find the linear speed of the moon. Express your solution in miles per hour. Let's ingest that for a moment. So, solution now. We have to consider the formula V is equal to R times omega, where omega is the angular speed. Now, what's the radius? The radius is 2.61 times 10 to the fifth what? Miles. Now, we want to determine the value for omega, and the angular speed, omega, of the object is what? Is the angle theta, measured in what? Radians. Theta is always measured in radians for this particular case. Now, swept out divided by the elapsed time of t. Now, omega again is theta divided by t. And remember, one revolution is equal to 25.1 days. Now, at some point, we have to do what? We have to change days, convert days to hours. So remember your ratio. One revolution is equal to 25.1 days. So that means that 2 pi radians is equal to, in this case, or divided by 25.1 days. Now, in order to convert this to hours, we want to take 25.1 days and times it by what? One day being equal to what? 26 hours. We're going to multiply days right here. Well, this is the ratio here. Let's talk about that first. The ratio has to be set up to where we said the other day that the ratio, whatever you're trying to get, whatever you're trying to have the units in, whatever units in, whether it's miles per hour or days per hour, you have to have the unit that's on top. That's the one that's going to be the actual thing that you're looking for, and everything else what? Cancels out. Now, in this particular case, we want miles per hour, so days are going to have to cancel out. So 25.1 days times 26 hours divided by what? One day, this cancels out here. So 25.1 times 26 is going to equal to 652.6 hours. So in this case now, 2 pi radians, one revolution in this case, is going to be equal to 652.6 hours. So this is a ratio, this to this, right? As you see. So we go over here, we put this here. Of course, we continue writing this. 2 pi radians divided by 652.6 hours reduces down to, we have to always reduce to the lowest term, which will be pi radians divided by 326.3 hours. So now what we do now, we can plug this all into the formula. Now we got the angular speed established. Now we're going to take 2.6, the radius, 2.61 times 10 to the fifth mile, and times it with the angular speed here. And of course, pi is rounded to 3.1416 radians, divided by 326.3 hours. And when you multiply this, this is going to become 2,513 miles per hour. Remember, if you have any questions or if you're stuck, just make sure you go back and rewind the CD, rewind it and study it, and go through the steps and listen to the tape or listen to the CD very, very closely. And you will know how to calculate the linear speed on the moon, the linear speed on the earth. Thank you.